Okay. Let's continue from there. That was our countdown. It's like very basic example of a recursion. And then we have calculated sum of a list of numbers, just what we have done manually in our paper and pencil. We're starting from here, either from the beginning or from the end. Like in this particular example, I have calculated from the end. Since it is the list, we can pop the list item from the last. Whenever it's popped up, we are adding to the accumulator and then adding one after another to the very end of the very last item of the list. Whenever we have no more item, then we're done, right? That's what we have done. And then we talked about the recursion, not the recursion, factorial. But the factorial is a mathematical problem. So when it's like n factorial, it could be like 5, 6, 10, whatever the number. It is like that number multiply forwarding the decreased number until 1, right? So n factorial is like n minus 1, n multiply n minus 1 factorial. So for the n minus 1 factorial, it should go all the way to 1. So we have a terminating condition. It's like whenever we have 1 factorial, we're done. It's like n factorial is like n multiply n minus 1 factorial. When you don't know n minus 1 factorial, we need to create this one, n minus 2 factorial. For the n minus 2 factorial, this n minus 2 multiply n minus 3 factorial, so on and so forth. So for an example, 5 factorial, we have used 5 multiply 4 factorial. We don't know the 4 factorial. That's why it's 4 multiply 3 factorial. We don't know 3 factorial. So 3 multiply 2 factorial. We don't know 2 factorial. So 2 multiply 1 factorial. We don't know 1 factorial. 1 multiply 0 factorial. Yes, we know the 0 factorial. So 0 factorial is 1. So 1 multiply 1 is 1. We're replacing 1 factorial to 1. So 2 multiply 1 is 2. We can replace 2 factorial to 2. 2 multiply 3 is 6. 3 factorial is 6. We can replace it by 6. Then 6 multiply 4, 24. We can replace by 4 factorial to 24. 24 multiply 5 is how much? 120. So then you can replace 5 factorial to 120. This is how we can calculate in a naive way, right? Now, why it is a recursive problem? So one of the important thing of a recursive solution or the recursive problem is like if we can make a self-similar thing, like similar thing doing again and again, just like this. For the 5 factorial, we're doing 5 minus 1 factorial, 4. For the 4, 3. For the 3, 2. For the 2, 1. So on and so forth, right? Now there are 3 major rules of a recursion. Those 3 laws are: it should have a base condition. What is the base condition? Like a terminating condition. In our case, our terminating condition is like 0 factorial. We know our known case is like 0 factorial is 1. Whenever we have a 0 factorial, it is 1. So we need to go deeper until we have 0 factorial. So this is our base case. What is the second thing? A recursive algorithm must change its state and move forward. Well, we are forwarding in backward way here. So we're changing our state, but going backward and mainly going forward to our base case in that particular way. But actually, we're going backward here. So forward or backward, it doesn't matter, but it is going forward or it is moving toward to the base condition. And the recursive algorithm must call itself. You can see here, we are calling this factorial. Factorial is the function. We're calling the factorial for certain number, 5, 4, 3, 2, 1, but the function is factorial, right? Okay, those are the three main laws to solve the problem in a recursive way. Now going back to our factorial problem, how we can solve this problem? We need to create a function so that it can call by itself, right? What is the function? The n factorial is n multiply n minus 1. So we can write a function like factorial here's our function like def factorial fact. Whenever we have n multiplication of calling itself, calling the same function factorial, but with a lower number. Right? This is a very simple function. Now the question is, if we're writing this function, though it's like one line of function, like one line of function body, it will call again and again, like unlimited time, infinite time. Why? As we don't have any terminating condition here. So three important things is like it should have a base case, it should call by itself, it should go towards the base case. So it is going like decreasing again and again. On the next run, the n value is n minus 1, right? On the next run, n value is n minus 1. This value will be like n minus 1. This n actually n minus 1 actually n minus 2. When we're calling with the n minus 2, then n will be n minus 2. Then this n will be n minus 2. Now this n will be n minus 2 minus 1 is like n minus 3, so on and so forth. But it will go forever if we don't have any base condition. We should have a base condition. So this is not a recursive solution. It's because it doesn't follow those three rules. What are those three rules? It should call by itself. Yes, it is calling itself. It should going towards the base condition. I'm not sure whether it is going towards or backward, but at least we're changing something. Somehow it is okay, but we don't have any base condition. In that particular scenario, it is an infinite recursive problem. Infinite recursion, just like our infinite loops. In the infinite loop, if we don't have any exiting criteria, it will call again and again and again, right? So to avoid this type of situation, infinite recursion, we have to have a base condition here before we call the function or somewhere. What is our base condition for the factorial? Whenever the n value is 0, we can return 1, right? So let me draw the stack diagram again. Stack diagram, not the stack. So we're calling the function factorial n. In our case, it is factorial 5. It calls here 5 multiply factorial 4. For the factorial 4, it calls 4 multiply factorial 3. For the factorial 3, it is 3 multiply factorial 2. For the 2, it calls 2 multiply factorial 1. For the factorial 1, it is 1 multiply factorial 0, right? And our base case is whenever it's 0, it returns 1, right? So this is the call stack. Have you heard the term Stack Overflow? Is the well-known website. So basically, whenever we are calling again and again for an infinite recursion, basically the error is Stack Overflow error. From there it came, the Stack Overflow. So we cannot call a function that many times so that it overwhelms the memory of our computer system. So we need to avoid this type of situation. The good thing of this Stack Overflow is like in our computer system, there is the limited memory for the function calling. Like our infinite calling, there is no limit. It can run unlimited time. But in our computer, I'm not sure what is the stack size, probably 30,000 or 10,000. I'm not sure what's the exact number. Until that time, it just terminate the program. So if you don't have any base condition, your program will not run. It will stop at some point. But we have our base case here. Whenever we have a 0, whenever the n value is 0, then it will return a value. That means we're done with this function calling. So we can return from here. So let me write the code again here. So the code was factorial is the def factorial n. Our main return thing is return n multiply n minus, actually not n minus. We're calling the same function fact n minus 1, right? And before that, we have a base condition here, like if n is equal 0, we are returning 1. Now, let's dig down for the F5. N value is 5. Here, 5 multiply fact 4, right? It goes here. N value is now 4. N is not equal to 4. We don't need to do anything. For this fact 4, we're calling 4 multiply fact of 3. It goes to here again. 3. N is not equal 0. For the fact 3 is 3 multiply fact 2. We're calling it again. 2, n is not 2. So 2 multiply fact 1. Again call with 1. N is not equal to 1. So we call it here again 1 multiply fact 0. Yes, now we call with fact 0. Now it matches. N is equal to 0. It returns 1. That means this function returns 1. That means we're done with this function. So whenever we're done with this function, we can replace the value 1. So 1 multiply 1, 2. We're returning that particular function calling. Like we're done with the fact 1 function calling. It returned 1. Then 2 multiply fact 1 is 2. Fact 1 returns 1. So 2 multiply 1 is 2. That means the result of fact 2 is now 2. We're done with the fact 2. That means we're keeping the stack one after another. And then when you're done, we're removing from the stack. So first, fact 5, then 4, then 3, then 2, then 1, then 0. When you're done with the 0, we're removing this function call from the stack, then going upward. Fact 1 done with this one, done with this one, so on and so forth. Now, still we have fact 3 and fact 4 and fact 5 in the stack. So fact 2, 6, it returns 6. 4 multiplied 6 is 24. So we removed until 4 up to this point. Then we only have fact 5 in the function stack. So 24 multiplied 5 is like 124. So we're done with the function stack. And then we're returning the value. This is how it works with this only 3 lines of code. We're writing only 3 lines of code, but in depth is like a long stack, depending on the number of n. If it is like 20, it will have like 20 functions. If it is like 50, it will like 50 functions. Right? Does that make sense? So it is important to investigate the code in the Python tutor to know what it is doing. So this is my fact n. I'm returning n multiply fact self-calling n minus 1. I don't have any base case, so make sure you write some comment. This is our base case. If n is equal 0, return 1. And this is our recursive case. Okay. Now, if I'm calling this function fact 5, you can see here
this is our first function, fact 5. Here is our function stack, first function stack. Then again another function stack, 2, 1, 0. So you can see here, these are the stack of function 5, 4, 3, 2, 1, 0. So at the 0, we can return it from here. So we're done with this one. We can return from here. You can see here return value. That means we're done with the fact 0 function calling. When we're returning, we're removing those things from the stack. It returns to the fact 1. We have some value. We remove this one from the stack. Then we have 2. 2 multiplied 3 is 6. Then we're done with the fact 3. We're done with this one, 24. Then 120. And then when we're done, we return the result. So we haven't printed it here, so it is not printing anything. This is how it works with those small lines of code. So it is like 3 lines of code, but in depth, it is like too many function stack depending on the end value. So when you're not sure what is going on, then it is the best option to go through the Python tutor to investigate your code. Okay. How many of you know the Fibonacci number? All of you know? Okay. So Fibonacci, let me go through some history of the Fibonacci. I already have discussed the infinity recursion. Fibonacci sequence is like this sequence, starting with 0 and 1, then add by last 2 numbers to create the next one. So 0 plus 1 is 1, 1 plus 1 is 2, 2 plus 1 is 3, 3 plus 2 is 5, 5 plus 3 is 8, so on and so forth. So if I generate 100 Fibonacci number, it will be that long. Okay. Now the history of Fibonacci is starting from the Indian subcontinent. So on the 16th century, what's the name? Virahanka started the counting pattern in poetry, described the recurrence equivalent to function of n is equal to function of n minus 1 plus function of n minus 2. Like current number should be the addition of last 2 numbers. Then in 12th century, like after 600 years, Gopala and Hemachandra extended and popularized the same idea in counting syllable pattern and other combinatorial problems. So they call it like Virahanka number or Hemachandra number. Like in Indian subcontinent, Fibonacci number are called like in Hemachandra number. But there is like after 12th century in Europe, the Leonardo of Pisa, known as Fibonacci, he commercialized this number as a valid number or with some mathematical numbers. So we are well known with the Fibonacci number after like 12 centuries, but they're the same at Hemachandra number or Virahanka number. Okay, that's a short story. And that was first introduced on the rabbit reproduction problem, like how many pairs of rabbit can be produced in a year for one pair, given certain breeding rules. So the sequence arises like this, starting with 1 pair, then on the next year is 1, the next following year is 2. So 1 plus 1 is 3. Like they have their parents and 2 pairs, 3, then parents and subparents, and the following pairs like grandparent, parents, and the child, so on and so forth. So over the year, it increased by a Fibonacci number. Okay. Now, for the Fibonacci number, the question is, can we solve this Fibonacci number using a recursive problem, recursive solution? So think about this. I would like to know the Fibonacci number of 35. What is the 35th Fibonacci number? Well, I need to know. So with this Fibonacci, Fib, n is Fib n minus 1 plus Fib n minus 2, right? That means for the 35 of n,
we need to know 34th and 33rd, right? If we don't know 34th, that means you need to know 33rd plus 32nd. Same thing for the 33rd. You need to know 32nd and 31st, right? So on and so forth. Now the question is, when you will stop? Is there any way that we know some number? Well, we know some numbers, like first two numbers. First one is 0, second one is 1. That means Fibonacci first is 0 and Fibonacci second is 1. We need to go down all the way to 0th and 1st. Whenever I have the 0th and the first, then I can go forward. So let's calculate the 5th number. So Fibonacci 5th. So 5th is the summation of 4th plus 3rd. I don't know 4th, so 4th is 3rd plus 2nd, and 3rd is 2nd plus 1st. I don't know 3rd, so 2nd plus 1st. 2nd, I know the first number is 0 and second number is 1. So for the 2nd, I can replace with 1. For the 2nd, I can replace with 1. For the 1st, I can replace with 0. Same thing here. For the 2nd, I can replace with 1. For the 1st, I can replace with 0. Then all of the other things. There is the 3. Okay. So if I write the Fibonacci number 0, 1, 1 plus 1, 1, 1 plus 1, 2, 2 plus 1, 3. So this is the first, second, third, fourth, and fifth. So fifth number is the 3. This is how we can calculate. Now the question is, can I solve this problem in a recursive way? What are the 3 laws? 3 laws are, it should call by itself with some pattern. Well, I can see the pattern is whenever I am looking for nth number, I need to know n minus 1 and n minus 2. Right? Same thing for n minus 1, n minus 2, and n minus 3. So on and so forth. So this is a recursive pattern, same pattern we are calling itself. This is the first law. The second law, do we have a base case? Yes, we do have base case, but in this particular scenario, we have 2 base cases. Whenever it reaches the first number, the value is 0. Whenever it reaches the second number, the value is 1. So previously for the factorial, we have only 1 base case, like 0 factorial is 1. But in this case, we have 2 base cases. That means some base cases. And what's the third thing? We need to call itself again and again with some pattern so that it can move towards the base case. Yes, we're doing so. For n, it is n minus 1, n minus 2. For n minus 1, n minus 2, n minus 3, so on and so forth. That means we're going towards the base case. That means we can solve this problem in a recursive way. Right? Are you all agree with me? Okay. So now write the code here. So this is my Fibonacci number, Fib n. I need to return Fib n minus 1 multiply Fib n minus 2, right? This is my function calling, like calling itself with some pattern. The first thing. Second thing is like calling itself. Third thing is we do have a base case. Unless we have any base case, it will call forever. Not forever. Actually, in this particular type of scenario, we have a stack overflow error. Whenever we have a stack overflow, it will terminate. So we have to have a base case. What is the base case? Whenever the n value is 0, return. Actually, it depends if you are like considering n is like a first number, we can say here like n is 1 and it returns 0. n is 2, return 1. If you think n1 means like first number, if you see like n0 is first number, then it will be different. Either one, depending on your implementation. So what you're thinking here, n1 is like first number, right? So these are the base cases. Does that make sense? Any question? Now, what is the call stack of Fibonacci 5? For the Fibonacci 5, we need to call Fibonacci 4 and Fibonacci 3. So actually there are 3 stacks. This is the first level and those 2 things are in second level, right? Then we need to call this one first. So instead of writing this way, I can draw a tree. This is Fibonacci 5. We need to call 2 functions, Fibonacci 4 and Fibonacci 3. For the 4, we need to call Fibonacci 3 and Fibonacci 2. For the 3 again, we need to call Fibonacci 2, Fibonacci 1. For the 3, it will call Fibonacci 2 and Fibonacci 1. For the 2, I know the 2, 1. I know the 2, 1. I know the 1, 1. Right? Now, if we replace this value from the return statement as a base case, Fibonacci 1 is what? 0, right? Fibonacci 2 is 1. So 1 plus 0 is 1, right? Fibonacci 2 is 1. Fibonacci 2 is 1. Fibonacci 1 is 0. So here 1 plus 1 is 2. 1 plus 0 is 1. So 2 plus 1 is 3. Right? This is how it works. Now, think about, we have Fibonacci 6. What is the Fibonacci 6? Fibonacci 5 and Fibonacci 4, right? So for the Fibonacci 4, we can do the same whole thing to here. Right? For calculating Fibonacci 6, we need to calculate Fibonacci 5 and 4. And you can see here, for Fibonacci 5, we're doing the Fibonacci 4 thing here. Same thing for this part. Fibonacci 3, we're calculating the whole Fibonacci 3 here. Like repetitive things. We're doing the same thing. Okay? Now, we have now only Fibonacci 6, but if it is like a bigger problem, like Fibonacci 20, then it will be a long tree, but some redundant things. We don't need to calculate the Fibonacci 4 again and again for this particular case. We already have done these things. So this type of problem is like this type of solution is an exponential solution. Like over the time, it grows exponentially. The first 2 case is fine. Then for next onward, it is growing by 2 power of n. So if you calculate those numbers, for first n, it has like 2 power of 1. For 2, it is 2. 2 power of 3, 2 power of 4, 2 power of 5, like multiply by 2. For first call, it is only 2. Second call, 4. Fourth call, or the third call is 8. Fourth call, 16. Fifth call, 32, so on and so forth. Like for only one extra calculation, you need to call the function twice. That means over the time, it grows exponentially. It takes longer space to your memory, and it takes longer time to calculate. Now, let me write this code in here. I have the code here, I think. Yeah.
Here's my Fibonacci number n, and I'm returning those things by default. And these two are base cases. So what I can write here, this is my base case. Okay. Can anyone, okay, no, not this way. If it is I'm starting from 0. 0 is the first number. Okay. Can anyone rewrite this code in one single line? Like there are two base cases. Can you write one single base case so that it can satisfy both cases?
If less than 2, return n.
Great. So if the n is less than 2, we're returning the n. What's going on?
Where your enter is trying to run the code.
Okay. If the n is less than 2, we're returning n. This is our base case. It satisfies the both cases. If it is 0, it returns 0. If it is 1, it returns 1. Right? Otherwise, it can return those things, like 3 lines of code. If you're using n0 is like first number. If you're using n1 as a first number, then it will be different. You need to write this way. That's why people are writing this way. Or if it is less than 1, it returns n.
The return at the bottom, would that need to be n plus fib n minus 1? Or would
Well, if n is not less than 1, goes here. If it is less than 1, it returns from there. We don't need to write an else here.
Well, yeah, we don't.
not,
Do we?
well, not the else, the other return, wouldn't it need,
This one?
yeah, wouldn't it need to return n plus fib n minus 1 instead of this one?
This one, n minus 1? Yeah.
Wouldn't
And here is n minus 1 and n minus 2 for all other cases.
it-
You get it?
I just thought the equation.
Okay, so let me run this code in a Python tutor. So whenever you don't understand the code, it's better to run this code in the Python tutor. So you investigate in detail. Okay. Okay. For first case, Fibonacci 6. This is Fib.
Step 2 of 102.
Yeah. So n is not less than 6. It goes directly here. To what? Call 5 and 4, right? 5 and 4. Actually, whenever we are calling 5, we're not going to 4. We need to call the 5 first, then go to the next level. So for the 5, it is not less than 5. It goes directly here. It calls 4. Again, 4 is not less than 1. It calls 3. 3 is not less than 1. It calls 2. 2 is not less than 1. It calls 1. Well, in that particular case, we are in the base case. We're returning 1. Right? We're returning back to here. Okay. So let me write these things here so that it makes more sense. So Fib 6, Fib 5 plus 4, right? So since there are like two function called, we're not calling two at the same time. We'll call this one first. Fib 4 plus Fib 3 So since we have two functions, we'll call this one first. Any question given?
Oh, sorry.
So for 4, we'll call fib3 plus fib2. Again, there are like two function call. We'll work with only one function call. So fib2 plus fib1. Again, we have two function call. We'll work with only single one. Fib2 plus 1. Fib2 is fib1 and fib0. Since we're using n0 is the first number, so we have our very base case here. Fib1. Fib1 is what? Fib1 is 1. We're not working with the fib0 right now. It's because we're calling from the first one. This one, then that, then this, then 2, then 1, right? So we're at fib1 right now. We'll go back to fib2, but fib2 has two items, fib1 and fib0. We're done with fib1, then we will work with the fib0. Actually, fib1 is 1, fib0 is 0. Now we can calculate those two things. 1 plus 0 is 1. Now we're done with the fib0 is 1. Right? Then we'll go back to fib3, but fib3 has two items, fib2 and fib1. We have only calculated fib2. Now we'll investigate fib1 thing. What is the fib1? It returns 1. So 1 plus 1 is 2. Now we're done with fib3. It is 2. We'll go back to fib4. So for the fib4, it has two parts, fib3 and fib2. We're done with fib2. Now we will go to the fib2. Fib2 is fib1 plus fib0. Then we will work with the fib2, like one at a time. Okay? That's why you can see it has like 102 steps. It will call one after another with this sequence. So I think it's worthwhile to see all of those things by yourself, not in this class. How these 102 steps are going on. Maybe draw this type of things and start with here. Well, starting from here, 6, 5, 5 plus 4, 4 plus 3, 3 plus 2, but we're not working with fib4 right now. We're only working with fib5. We'll go down, call fib4. You can see here. For the first one, N6, it has fib5 and fib6, but we're not working on fib4 right now. We are working with fib5. Then it goes to the fib5. Fib5 has two parts, 4 and 3. We're not working with fib3 right now, fib4. So let me change this value to a smaller number so that we have lesser number of iteration. So for the 4, it has 3 and 2, right? We're only working with 3. We're not worrying about 2. For the 3, it has 2 and 1. Starting with 2, I'm not worrying about 1. It still have 1 here and 2 here. We're not worrying about those things. Fib2 is 1 and 0. We're not worrying about 0, just 1. For the 1, we have some value. We're returning from here to fib2. So for the fib2, we have done the first part, fib1, not the fib0. So it returns fib1, now it's the fib0. For the fib0, we have some value. What's the value? 0. Now we're done with those two, fib1 and fib2. For the fib2, you can add those two numbers and return a 1. Now we're done with fib2. So for the fib3, we have 2 and 1. We're done with fib2, not the 1. Now it will call fib1. Fib1, it goes to the base case. The value is 1. Now fib1 and fib2 value will add and then return to fib3. Now for fib4, we have two parts, fib3 and fib2. Now we're done with fib2. We're still working with fib3. Now we'll start with fib2. Now it will call fib2. For fib2, 1 and 0. 1 first, 0 later. For 1, it returns 1, then 0. 1 and 0, 1. We're done with fifth 2 right now. We have already done fifth 3 and fifth 2. We can add those two numbers to return the fifth 4. That's how it works. For only 4 Fibonacci number. So if it is like 6, it will grow exponentially. That's what I'm told. Okay, let's rewrite this function. So Fibonacci def Fibonacci n. What is the recursive things? Return Fibonacci n minus 1 plus Fibonacci n minus 2. And what is the base case? The base case is whenever the value is less than or equal 1, it returns the n. That's it. Now print the Fibonacci number 6, for an example. What is the 6th Fibonacci number? 0, 1, 1, 2, 3, 5, right? No, 8. It's because we're starting the 0 as the first number. So 6 is the 7th number actually, right? So we're actually looking for the 7th number. 0 is the very first number. Like in the Fibonacci list, what is the 6th index? Any question? Now, okay, like any question? No? Well, definitely you need to run this code in a Python tutor to investigate how it's working. As I've shown you for the Fibonacci 4. You need to draw this type of things first, then go one after another, how it works. Unfortunately, in the Python tutor, it doesn't add the next addition. It just only works with the first one. And then when it is done, it goes to the next one. You cannot see this one and it is holding the other one. It is not holding anything. It's going deeper first. Like it is called like depth first search. Like depth first operation. It goes deeper first, then going to the breadth. Okay. Now it is okay to calculate the few numbers. I can create a range of 10 and it will print first 11 numbers, actually 10 numbers, starting with 0, ends with 9. These are the 10 numbers. How about 20 numbers? It can generate 20 numbers. I need to print those things in a list so that it is more easier to see. So F list. I need to add things to the F list. Dot append this, and finally I'll print the F list. Okay. So these are the 20 numbers, first 20 numbers. I'm increasing to 25 now. Okay. Then 30. You can see it is taking a little bit longer. If it is 35, it is not running. It's taking longer time. Well, maybe starting with 31. For 31, it's a little bit longer. How about 32? Takes more time, is because it will grow exponentially, like 2 power of 31, then 2 power of 32. It is like 2 times of the time what it takes for the previous one. Now, if it is 33, it's going a little bit longer, still loading. But if you're going beyond 40, probably need to wait for a longer period of time. Like until 40, it is okay for this type of computer. Whenever it goes beyond 40, it is taking longer and longer. Now the question is like, then how I have generated this 100 Fibonacci number for you? Did I run this code for the whole night and find the result in the next morning? Or if someone asks you, can you find the 1000 Fibonacci number? Probably need to wait until the Artemis return from the moon. Right? This is not the case, right? So we have to solve this problem in a different way. This is the naive way, but this is not the only way to solve this problem. Now the question is like, you are teaching us recursion. You told me we can solve this problem in a recursive way. Now you're telling me we can solve it in a different way. But the different way, in a sense, when it is growing bigger and bigger, then somehow we need to shut it down. As I've shown you, this Fibonacci 4 calculation is redundant. We can skip this redundancy. We're calculating Fibonacci 4 twice. Now, think about like Fibonacci 35th number calculation. So 35th is 34th plus 33rd. For 34th, it is 33rd and 32nd. And that will be a big tree for the 32nd, third, right? Now, if it is taking a longer time, we can skip that longer time to here. We don't need to calculate it again. We can skip this time. For our code, what I have written here, it is calling again and again. For this particular case, 33, it calls 32nd and 31st. For 32nd, it calls 31st and 30th. When it is done with all of those things, then it's still starting with the 31st calculation. That's why it's taking longer time. We can resolve this problem by removing the redundancies. If there is any redundant things, we can skip it. Does that make sense? How we can make it better? Now, what is the approach? Or how we can solve this problem in a better way? Any idea?
Saving the 34th or the 33rd in a dictionary.
Yes, by saving those pre-calculated things in a storage, a dictionary, what we have learned, right? And what else? Chocolate, right? So what you can do, whenever we have something there, or whenever we're calculating something already pre-calculated, then we can just get that information from the storage. Otherwise, we can calculate it. So for an example, whenever I'm calling the n-1, I'm not sure whether the n-1 is there or not. So what you can do here, we will check if the n-1 is already calculated. If it is calculated, then we don't need to calculate it again. We can return that value. Otherwise, we need to call this Fibonacci number, Fibonacci calculation. And what Gavin said, we can use a dictionary to store it. So what I can do, we can use a dictionary here. This is our dictionary. And what it will store? The key value pair, right? What are the key value pairs? Maybe we can skip the base cases to there. So for the 0, this 0, for the 1, it is 1, 2 base cases, right? Now, in this particular case, if n is less than 1, how we can rewrite this code? So we have our dictionary. Right now, we're not returning the value. We're returning the dictionary values. So now, if the value is less than or equal to 1, what do you return from the dictionary?
The value of that, so D1 and then brackets and.
The n, right?
Yeah.
Instead of just the n, I have those information in the dictionary. So I need to, sorry.
No, that's it.
So I need to return those things in the dictionary. Now I told you I need to check these things in the dictionary, n minus 1. So I'll check if the n minus 1 is in the dictionary. If it is there, then we need to return the dictionary values. Otherwise, we need to call it. Does that make sense? That means we can minimize these things. Like whenever we're calculating 31st again, we'll check the dictionary. If the 31st is already in there, we have already calculated it. So we don't need to do all those things function, all those function calling. We can just return that value. It saves a lot of time, like half of the time, right? So if the n minus 1 is in the dictionary, if the n minus 1 is in the dictionary, we're returning that value. So right now our key and the value, so we're starting from the 0. That means n minus 1 is the n minus 1 item in the index. And this one is the value, associated value, right? Same thing for the n minus 2. If it is n minus 2 in the dictionary, then we will return the n minus 2 items. Otherwise, we need to call the function, right? Does that make sense, Carter? Did I miss anything? Stephen, did I miss anything? Anyone? So what I have done here, whenever I have this value in the dictionary, I'm returning this value. But our dictionary is only 2 items. If we don't do anything, it never finds this way. It's because nothing is there. It always calls the fib n minus 1. So what I'm trying to say, whenever we're calling 31st, we're calculating 31st, make sure after calculating 31st, we have to store that information to the dictionary. So that in the next run, whenever we're calling, is it there? Yes, it is there. Otherwise, it keeps calling. That means whenever we're calling this one, we need to store that value to the dictionary. Right? Then in the next run, it will find this value. Same thing for the N2. Make sense? And now, instead of this function call, we can return our dictionary keys. So what it means is like we have been stored those values after calculating the N1. So that in the next run on the N1, it never calls this one, it just returns the value. Let's see if it works. It always store 111. There should be some problem. N minus 1, N minus 2. So starting with small number 5, it goes here. Okay. This is the best way to debug your code. I will call Fibonacci small number 4. And see how it works. Okay, now he has a dictionary 0, 0 and 1. Call fib4. It checks if it is less than n, it will return that value, but we don't have anything like it is not less than 4. It goes to here, n minus 1. Actually, we're looking for 4. We're on the fib4. We're looking for 3. 3 is in there. No, it is not. We're calling 3. It calls fib3. Well, start with this one, 2. 2 is in there. No, it is not there. Call 2. Now 1. 1 is there. Yes, it is there. Oh, it is there. Oh, actually 1. 1 in the dictionary. Yes, it is. Return 1. Right? Then n minus 2. 0, right? And you can see here it updates the dictionary, but it updates wrong. It's because it should be fn minus 1 plus n minus 2. That's why it returns the wrong one. So it's n minus 1 plus fib n minus 2. Okay. Actually, we don't need this one. Let's see. Again, 4, 3, 2, 1 is there? Yes.
I think what's going on is, okay, let's run this first, actually.
Yeah. So 1 is there. Return 1. Then the next run, fib 1. 1 plus 1 will be 2. What's the problem? 0, 1, 1, it should be 1, right? Yeah, what is the problem, Lucas?
What I was, I'm not sure actually how this is causing the problem we just saw.
Okay,
But
let's run it slowly. Fib 4 goes to here. Fib 3 is not there. Now it calls fib 2 and fib 1, right? So 2 is not there, so 1 is there. So it calls fib 2.
So, and then it goes to 1 again because we did it. If n1 is in the dictionary.
And 1 is no. So right now we have 3, right? So 3 is not there. It calls 2. 2 is not there. Is not there. Now it calls 1.
It's adding 1 because you're doubling the subtraction when you subtract by 1 in the if statement, because you're already looking at the previous one when you
The
called it
division
with
between
n
n minus 2 and n minus 3.
Yeah.
Okay, I think I have the solution here, so it's better to go through the solution. It's k minus 1, k minus 2. So actually not n minus 1. It is like n, then n minus 1, n minus 2. So let me call this one.
You're subtracting it additional time.
We're subtracting twice.
So you're subtracting in the call and in the conditional.
Okay. So memo is like a dictionary. So this particular like approach is called memoization. Like in a memo, we can write those things. If it is there, we can find it there. So this particular approach is called like memoization. So it's a dictionary, nothing but a dictionary. So it goes to there. If k is in the memo, return that value. If k is less than 2, we are putting that value to that memory, like the dictionary. Otherwise, it calls k-1 and k-2 to calculate and then store those values to here. And finally returns the particular things. So we need to call fib 5, for example. 5 memo is empty. We're not putting 0 and 1 there. So calling fib, k is 5, right? 5 is not in the dictionary. 5 is less than 2, no. Else it calls 4 and 3. Calls 4. 4 is in the dictionary, no. Is less than 2, no. It calls 3 then. 3 is not in the memo, not is less than 3, then it will call 2. 2 is not in the memo, not is less than 2, it will call 1. Now it is not in the memo, but it is less than 2. Now we can put that 1 to the memo. You can see in the memory we have 1, 1. That means 1 is the first item, not the 0. Then we have this one here, right? Come to here. 1 and 0 is there. 1 and 0 is 1. So for this 2, this function called 2, it will add 1 and 0 to 1. Then it will go back to the next one. Next one is k1. K1 is already there right now. It will add 1 plus 1, 2 for the third one. For the third one, it will add 2. Then we're done with the third one, it will call the second one, F2. F2, we have those two things, 1 and 2 here. So we don't need to call those things. We can just return those two values and return 1. For the 4, it just added 3 plus 1 is 3. We're done with the fifth 4 for this part, then we need to call the fifth 3. We don't need to call the fifth 3 again, it's because it's already there. We can skip that redundancy. So just add 2 plus 3 to 5. Now, if I run this code for see the difference. So this is our previous one. So it took for 33 calculation a longer time. If it is going 35, it is not a blink of eye. It is taking a longer time, couple of seconds. But if I can rewrite this code with memoization, then probably it takes lesser time. I'm printing this one to 35. I'll make sure I need to use a for loop for I in range of 35. If I make sure I have a list here, and I can add that item to the list. And finally, I print the list. So, okay. Let me see. Memo return, blah, blah, blah. Okay. It's time to call. It's taking 35 numbers, but every time, oh, it's under the loop. That is the reason. It's a 35 number. Now, if it is like 100, it will not take that long time. You can see 100 numbers. Because we have already calculated those things. The longest one is like for 100 calculation. We have 99 already in this dictionary, 98 already in the dictionary. We don't calculate the 98 and 99 every time. So this particular approach is called like memoization. Okay, or it's called like top-down approach. Also it's called like dynamic programming, DP. In the advanced programming, you will learn DP. This is one of the good example of DP, dynamic programming or memoization. So whenever you cannot solve anything, start with the recursive problem. If it is going bigger and bigger, change it to like whenever you are calling, see if it is in the dictionary, if it is there, don't call it. Saves time. This is the memoization. There is another approach which is called like bottom-up approach. Now, as a human, if I ask you what is the sixth number of Fibonacci, how can you calculate it? I need to know fifth and fourth. I don't care. I should start from beginning. I know the Fibonacci start with 0 and 1. What is the third number? 1 plus 1 is 1. What is the fourth number? 1 plus 1 is 2. Then 1 plus 2 is 3. 3 plus 2 is 5. 5 plus 6 is 8. So this is the way we can solve. So this is called like a top-down, like bottom-up approach. We're starting from the bottom, from the base case. Or it can be called like iterative way. We're starting from the beginning, not from the end. We know those two base cases, we can add up how long it will take. And how long it will run? That many times, 6 times we need to add. So this is called like iterative approach. We know first two base cases. The second one will be okay. We can rewrite this code in this way. So I have two numbers, first and second, right? I can say first and second. So for the very beginning, the first number is 0, second number is 1. What is the third number? 1, right? On the next run, the first number is 1, second number is 1. What is the next one? 2. Then on the next run, we will update this one as first, this one as second. So 1 and 2. What is the fourth number? 1 and 2 is 3. On the next run, we will update this one, 2 and 3. Then it will add 5. The next run, we'll just move these 3 here and 5 to here. So we're not using too many variables, just 2 variables. Previously, we have used a dictionary, which takes a longer memory for storing the value, but fewer call compared to naive way. But this time we're not calling any function. There is no function stack. Also, we don't have any memory location to store like a dictionary, just 2 variables. That's it. So here's the time comparison of all of those things. I have created a method. You can see here for the time comparison. This is our naive way. If it is less than 2, it returns that value, otherwise call that function. For the memoization, we have a memo or a dictionary. I can call it as a cache. If it is there, call that value. If it is less than 2, assign that value to the cache. If it is not there, then call that function. Only you will call that function whenever if you don't have this value to the dictionary or the memo. And this one is more iterative. Like we have only 2 variables, a and b, 0 and 1. How long we need to iterate? So this is 0 and 1 from second to n minus 1. Just replace this value. On the next run, a will be b and b will be a plus b. That's it. And if I use a time helper to call this function 3 times and get the average, by calling that many value, 5, 10, up to 45, it takes that many times. For the 5, naive way, it takes that second. So naive, memo, and iterative are somewhat similar. You can see where it is growing when 25th Fibonacci number, naive will take still lower. When it is 30, it takes like 0.1 second. But still for the memo and iterative, it is 0000, like 4018. When it is 35, 38, it takes 8 seconds. For 40, 23 seconds. For 45, it took 256 seconds. But still for the memo, it takes only 4034 seconds. And for the iterative, it takes like 503. It's because it is not using any dictionary. It is not using any function calling. Now, what do you think? What I have used for calculating the 100 numbers? The naive way? Probably not. I have used the iterative way to calculate the 100 numbers. But at least you need to know how you can solve this problem in a recursive way. This is what we have for the recursion. Recursion is like whenever you can see any problem that can be a self-similar problem, you can call it on that function again and again. And also, if you have a base condition, only then you can use the recursive problem. But in a recursion, it grows over the time. Whenever it is longer size n, then probably you need to think of using a dictionary to avoid the repetitive calls. This is called the memoization or top-down approach. This is very easy, like converting a recursion to memoization, but iterative is a different type of problem, like the solution. You need to start from the beginning. You need to start from the base case. So somewhat you cannot go to the iterative solution at the first point. It is easier to go to the recursive solution at the first point, then modify it to memoization. It is totally fine to solve a problem with the memoization. People are not expecting, like this is not too much in terms of 250, like 40 multiplied 3s because we're running 3 times. So 40 multiplied 3, it takes like 0.000034 seconds and 3 seconds, like 10 times faster, but with the sake of memory, not the function calling. A little bit function calling, but we don't have any function calling here. Okay, so you can see there's like definition of top-down approach and memoization approach, like top-down and bottom-up. So top-down is nothing but recursion, but you're using DP, the dynamic programming. But for the iterative, it is like a bottom-up approach, which is like an iterative problem. But we are not using any recursion. Start from the known base case and build a function n by repetitively applying the Fibonacci rule or in any other rules. So it is hard to find at the very first place, but I think recursion and then memoization is the better approach to solve a problem. Okay. Any question? It is an advanced topic. So yeah, you need to read this material very, very carefully to understand it very well. And whenever you can see there's only 3 lines of code, but it takes longer time. So you need to run those code with a small number of n in a Python tutor. Okay. So that's all for today.